All right, problem number 2. It's another area and volume between curves. This time we're given 2 separate curves, and we're going to solve it almost identically the way we did before. Again, we're working 2-dimensional Cartesian, so our differential is going to be the same, dx dy. When we're looking for the green area in between, so when we find for our limits, again, we're going to be 0 for the x value all the way up until where this point right here is, which is going to be 1. X equals 1, y equals 1. For our y value, it's going to be the bottom curve first, which is x squared, to our top curve, which is just x. We're going to set up the integral, just like we did before. And then you can go ahead and solve that. Okay, as you can see, the answer is going to be 1/6. Again, if you have troubles with the integration itself, reach out. We can talk about that math too, but it's a really simple, quick one. I'm going to go right on to part B, which is, again, we're finding volume around the x-axis. Just like before, we're going to use cylindrical coordinates. So our volume is going to be rho, d rho, dz, d theta. Our limits are going to be the exact same, except we're going to substitute x and y in for z and rho, just like we did before. So we have 0, z to 1, and then we're going to do this can be z squared to rho to z. And then when we set up our integral, it's going to be triple integration rho dz d theta 2 pi 0 0 to 1 and z squared to z. Okay, once you solve that integral, you'll find the answer is 2 pi over 15. If we go on to part C, it's going to be the same problem, just we're rotating around the y-axis instead this time, which means we're going to switch which variables we're changing. So y is now going to become z, x is going to become rho, and it's going to be the exact same problem once again. You're going to set up your integral, rho d theta dz. Let's flip those. dz d theta 2 pi 0. Your c is going to be from rho squared to rho, and then 0 to 1, and then go ahead and solve that integral. And as you can see, the answer is pi over 6. Again, I just want to highlight with these problems, it's very similar to problem 1. Obviously, you need to be able to do an integral, but the important part is being able to identify what kind of problem it is. Understanding an integration will give you an area under a curve, and being able to set your parameters and be able to pick what your limits are, and understanding how to set up the integral itself. So if you can explain that, that's the point of this. I'll go on to the next problem. All right, welcome back. Problem 3 gives us a polynomial expression and asks us to graph both that equation, its first derivative and second derivative. So this problem isn't testing whether or not you can take a derivative, but more testing your knowledge of utilizing those equations to find critical points on the graph that you're building. So the first thing you're going to have to do is take those 2 derivatives. So the first one is x squared plus 5x plus 6, and the second derivative is going to be 2x plus 5. So the first points we're going to find are the max and minimum points, which can be found by using that first derivative and setting it equal to 0. And then from here, you're going to solve for x. So after you solve, you'll find that you have 2 x values. One will be a minimum and one will be a maximum. And the next thing we need to do is plug back into our original y polynomial, and that'll give us the 2 y values for each of those coordinates. Okay, after you plug and chug, you can see that we've got -5 over 3 and -3 over 2, respectively, for each of our points. So this gives us 2 full coordinate points that we'll be able to put on our graph after this. But next, we need a little more information, and we're going to go down and we're going to find a point of inflection using the second derivative. Again, you set it equal to 0, and you just solve for x. X equals -5 over 2. And then once more, we're going to plug and chug and then finish that coordinate point. So after we plug and chug, we get -5 over 2 as our x-coordinate, and then -19 over 12 as our y-coordinate. The note I have on the right, it's a good check and ability to show your knowledge of concavity. So basically our point of inflection is where that concavity is shifting. So you can just test that by picking a number larger than above our point of inflection, and pick a number more negative than our point of inflection, and throw it into that second derivative equation. And you'll be able to see if it's a positive or negative number, shows concavity. So if you pick 0, which is greater than our point of inflection, you're going to get 5, a positive 5, so you are concave up to the right of our point of inflection. And then if you pick a more negative number, and then say -10, you're going to get a -15, which is concave down. So once you find all of your points, you're going to all put it on a graph. And I will say, your artistic ability isn't what's being tested here, but you should be able to put this graph together based on the points you've just found. So each of these points are the coordinates that we just discovered up here, and then you can draw the graph through it. Next, we're going to do this all again, but just for the first derivative equation. Okay, so for part B, we're building this graph for the first derivative, which is going to be almost the exact same process, but even easier. So we're going to take the second derivative, which is the first derivative of our new starting equation, and the third derivative, which is the second derivative of our starting equation. Second derivative, y double prime still 2x plus 5, y triple prime is just 2, which is really easy. It just means that we have a concave up graph. The 0 for our first derivative of this equation, which is the y double prime, is still going to be x -5 over 2. And now if we plug and chug that into this new equation, we get y equals -1 over 4. You can check me on that, but we're going to move forward. So basically what this does is gives us our critical point, and we do not know if it's a maximum or a minimum, and then that's where the third derivative, we have a concave up shape. So now we know this is indeed a minimum point. But we still can't quite build a good graph because we don't have any other points to put on it. So for a problem like this, the best thing to do is to find where we cross the axes if we do. So if we're looking for where we cross, say, the x-axis, we're just going to put in y equals 0 and solve there into our original equation. So if we do 0 equals x squared plus 5x plus 6, this is the same equation that we found before. So we're going to get x equals -2, and then x equals -3. And then those points are two more coordinates that we have. -2, 0, and -3, 0. And now with these 3 points, we can put together a pretty little graph. And now we have one more graph to make, and we're just going to go ahead and do it real quick, because we have y double prime equals 2x plus 5. And this is a line. I hope everyone can recognize that. It's in the simple line equation form. We have an x-intercept, a y-intercept right here. So if we plugged in 0 for the x into this, we would get 0, 5 as y-intercept. We can do the opposite, put in 0 for y and find the x-intercept. And that'll give us -5 over 2, 0. And then from here, we can make a graph. It essentially, this will not be to scale. It's just going to be a straight line like this, where this is 5 and this is 5 over 2. Problem 4 gives us this interesting looking graph with 3 separate line segment areas. And it asks us to sketch the first and second derivative on a graph. So I've translated it down into my own handwriting. It's more easily manipulated. This top red line is our original graph. The green y prime is our first derivative, and the pink is our second derivative. So I'm just going to walk through this real quick with you guys. It's pretty simple, but you could very easily get a question like this. So what's the knowledge that we're being asked is if we can communicate what the first derivative means to a graph above it. And simply put, the graph of the first derivative is a graph of the slopes along those points. So when you take that first derivative, the slope of this first line, it's at the y equals 1 mark, but the slope is 0 the entire time. So we just have a straight line along at y equals 0. The second bit is a semicircle. And at the first point, what you have is an infinitely positive slope that approaches 0 at this point of inflection right here. The slope approaches 0, and at this point it becomes negative until it becomes infinitely negative, which results in this graph right here. The third segment is just a straight line with a slope of 1. They tell us that by giving us this y and x change right here. And that gives us a straight line, but on y equals 1 for the second graph. You do this all again, the first and third segments become 0 because they're both straight horizontal lines. But what you have here is very interesting, is at the far left, you have an infinitesimally negative slope, and it's becoming less negative of a slope as you approach eventually 0. And on that note, this should be touching the black line right here, because at this point of inflection, right, the slope is 0. We have come all the way, and then it becomes straight, and then goes back down, becoming negative again, right? This is a zoomed in part of this middle bit, the green dot. So you have an infinitely negative slope, so this pink line is infinitely negative, and then it approaches, just kisses 0, and then again becomes infinitely negative again. And so we get this upside down parabola.